Hello everyone, and thanks for coming to this workshop where, as I said, my focus in this talk and the next talk will be more on the methods side. And here we are going to talk about the methods we developed as opposed to the methods in the previous talk, which are quite well-known methods of dealing with various diagnostics issues in Cox regression. The views are always my own, and basically our main interest always is to understand how various advances in medicine and in social sphere affect increases or changes, shall we say, in longevity. And in medicine, people are usually doing randomized control trials, which are considered to be the gold standard. So how does the randomized control trial works? First of all, they have very strict inclusion and exclusion criteria. Usually, they wouldn't allow patients with multiple morbidity. They won't allow very old patients. They won't allow patients who are taking lots of other drugs, and so on. And also, they can run a trial for a very limited number of years. 5 years if they're lucky and have funding for 5 years. Usually it will be 2-3 years. And what they do in a randomized control trial is they would randomly assign a person to either treatment arm or the control arm when they're comparing one treatment to another. And they usually believe that because they randomized people across the two arms, those two arms are more or less the same. And because of that, they don't need to do any complicated statistical analysis. They can just do, say, a t-test or something very simple, Kaplan-Meier analysis, two curves to compare the results of the two treatments. This may or may not be true. It depends how many patients are in the trial. But anyway, that's how the randomized control trials are done. And then if the results of several RCTs would show that the treatment works, NICE would consider it and introduce it into practice. And if we want to see then how this works, we would still need to wait for quite a long time to see whether this intervention works or not in the general population, which is very different from the population of the clinical trials. What we do instead is we are using the primary care data. In particular, we are using the database which is called the Health Improvement Network, or SIN. This data covers about 6 to 7% of the UK population. And it considered to be representative of the overall UK population. The advantage of using individual level medical data is that we can do quite sophisticated model, both of the uptake of medical treatments and the effect of the treatment on longevity. And we also can adjust for various individual socio-demographic factors and health factors. So we carefully design each observational study, say for each condition or each intervention. And we also try to match cases to controls. We do usually matching on the general practice, gender and age. Why we do this is because we believe that, say, in the same general practice, people are pretty similar. They live close to each other, they breathe the same air. There are many other factors which we don't have in our data, but which is similar for those people in the same GP practice. And also, last but not least, they have the same doctor, which can be equally good or equally bad for all of them. So there is quite strong effect of general practice there in the data. That's why we do this matching. So we get, say, one case and 3 controls from the same general practice. And then we would try to fit survival models, Cox regression, or something more complicated to this individual level data. And because of this, we believe that our conclusions are generalizable to the general population. As you already heard from Ilyas, the standard type of survival analysis, which is done in medical practice, is the Cox regression. And for the Cox regression, the second line shows that the hazard is factorized into 2 terms. The first term, mu naught, is the baseline hazard, and the second term is the risk score, which usually has a log linear relationship with the covariance. And we also were talking that if we take the hazard ratio, we would just add up with a number which hazard ratio won't depend on time, because the baseline hazards would just cancel out. So you saw this plot already, but this time I'm going to talk about so-called effective age, and unfortunately I discovered that the pointer doesn't work, and I don't have a mouse, so I'll have to do it kind of with my fingers. Okay, so let's look at the binary factor. For instance, here this is non-smokers at level 0 and smokers at level 1. So you can see 2 hazard lines on the log hazard scale. And they only differ by a constant, which is effect of smoking. Otherwise, they're parallel. So what I would do, I would try to look at the hazard for a smoker, which is my first green arrow, my left green arrow. And I will try to see at what age the non-smoker has exactly the same hazard. And I'll call that age an effective age. So here you see that actual age of a smoker is about, this is time after operation. So actual time after operation is 3 years. But for a smoker, the effective time after operation would be equivalent to 4.2 years if we compare them to the hazard for non-smokers. Does it make sense? Yes? Yes, I said that I can do it. I can find a unique effective age only if I have monotone increasing hazards. That's why I have done it on the right-hand side, where my hazards are monotone increasing. Otherwise, I would have found it on the left as well, perhaps. But we prefer to talk about the monotonically increasing part of the hazards. So you can see here that smokers' effective age for smokers is higher than effective age for non-smokers. And this difference, in general, delta, would depend on the time if our hazards look as arbitrary curve. Okay? So at each point of time, I can find an increment in age which corresponds to an addition of this extra risk, say risk of smoking. This is the idea of effective age. Other questions about this? Okay, let's move. Yeah.
Because the x-axis isn't age, is it?
This is log scale. No. Age actually is no, X, in this case, it's not age, it's time from operation. So once more, this is effective time, not effective age, for this particular picture. Sorry about this. Yes, but I can talk about effective time after operation for smokers as compared to non-smokers. Okay? And you can see that my increment may depend on time. Okay, so for an individual, the hazard ratio from the Cox regression can be easily translated into effective age if we know the baseline hazard. Of course, this is a big if, but we can estimate the baseline hazard from the Cox regression non-parametrically, and we can estimate baseline hazard by other means as well for different populations. So in principle, effective age is a very familiar concept for actuaries because many insurance companies are using kind of equivalent effective age as a way of applying correct rating to underwritten life. I know, for example, that various companies have their own name for effective age. I know that there is, for example, something which is called vitality age in Vitality, where they took in extra exercise people do, and they believe that that lowers age of the clients, that kind of thing. So the concept by itself shouldn't be very puzzling to you. Another nice thing about these calculations of effective age is that the hazards of mortality usually are pretty linear between the ages of, say, 50 and 90. This is the data from period life table centered at 2010. And we fitted two straight lines on the log scale to males and females. You can see that they're not quite parallel, but they are both certainly linear. And that means that the survival, our longevity, whatever, for English and Welsh population is well approximated by the Gompertz distribution, because the Gompertz distribution is a distribution which has straight lines on the log hazard scale. Okay? Of course, when I have straight lines, my calculations of effective age are much, much more simple. So you can see from that plot here what I'm doing. My first line, the baseline, is just A plus BT, straight line. And my higher line, say for smokers, is once more A plus BT plus beta, where beta is a log hazard, my coefficient from the Cox regression for that particular factor, say for smoking. So the distance between the two lines is just beta, that effect of my risk factor. And then it's very easy to figure out effective age from, for those two straight lines. And basically the formula is that difference in effective age, delta, can be calculated as beta over B, where beta is my log hazard ratio and B is the slope of my Gompertz log hazard. If we look at the population of England, one thing about this is that this increment delta for Gompertz distribution does not depend on time anymore. It's constant over time. So we can just say that if the Cox regression works and if the Gompertz distribution applies, our difference in effective age will be always constant over time. And for England and Wales in 2010-2012, the increase in the hazard between ages 50 to 90 was approximately 1.1 per year. So we can very easily calculate this delta, this increment in effective age for English and Welsh population. We'll take log hazard ratio, divide by log 1.1, and this is approximately 10 times log hazard, 10 times beta. Another thing which is nice for the Gompers distribution is that this difference in effective age translates to life expectancy. This is this lower formula there. Life expectancy for smokers at age t is the same as life expectancy for non-smokers at age t plus delta. This is what it means. So at first, when I have done that, when I noticed this, I thought that that's it. It's very easy. We now know that how much life expectancy will change depending on various risk factors. Unfortunately, when I thought a little bit more, I realized that this is not as straightforward as this. And this is because I don't know the baseline life expectancy. I don't know life expectancy for non-smokers. The only thing I know from my period life table is a mixture of life expectancies for smokers and non-smokers, because that's what my population is. So what I want to do in this talk is to tell you how to split this period life expectancy into life expectancies for subpopulations, which would be grouped by particular combination of risk factors. And then we could see how much actually particular risk would affect life expectancy of the population of interest. So this is what we are going to do here. Okay. So I'm going to look at a population which will consist of capital J risk groups. And the prevalence of those risk groups will be denoted by QJ. Sum of those QJs is 1. For instance, I am going to talk about cardiac risk groups. So I will have low cardiac risk groups, say medium and high cardiac risk groups, 3, J equal to 3. Okay? And my treatment of interest, for instance, can be uptake of statins. So when I equal 0, people are not taking statins, and when I equal 1, people are. Or it can be any other intervention, of course. So at each risk group, the uptake of treatment may differ, and we will denote this prevalence of treatment as PJI. So PJI is a prevalence of treatment I in risk group J. And then I can write my overall survival function for a population at particular HT as a weighted mean of survival functions in individual subpopulations. So I need to look at J times I subpopulations, and for each of those subpopulations, I will have a weight which will be just a proportion of a risk group and proportion of a treatment in that risk group. So this is this formula down there. I have just 2 sums there because I have binary treatment 1 or 0, but I could have more than 2 treatment groups. I can have capital I treatment groups, and then I would have capital I sums there. So overall, I would have I times J terms in my split of survival function into individual survival functions. And because I'm dealing with the thin data, I can estimate easily, I can find those weights. I can look at prevalence of treatment, I can look at the prevalence of risk. So I am able to feel the weights. My task at this stage is to estimate my individual survival functions. So how am I going to do this? Remember that our data comes from a Cox model. And the Cox model is very simple. It gives us a product of baseline hazard and a hazard which depends on the risk group, which denoted there by mu ij. And if I look at the log scale, my hazard, or my log hazard, will look like that. It will be some constant, A0, which may depend on the age I'm looking at. Then it will be effect of my treatment, alpha I. It will be effect of my risk group, beta j. It may be interaction between the two if, say, our treatment affects different risk groups in different ways. And it will be some other covariates which we will be adjusting for and which are denoted there by y. So this is how my hazard from the Cox regression looks like. And once more, if I fitted Cox regression, I know alphas, betas, and gammas. What I don't know is this first coefficient, A0. I don't know where my first baseline intercept sits. Okay, now this is a slide which I don't want you to dwell too much, because here I'm just looking at how survival function looks, so I'm exponentiating twice my log hazard. Let's not worry about this. Let's look at the lowest bit here. So the lowest bit is just this sum of individual survival functions. And as you can see, we have quite a few of things we know there. We know the weights, alphas, betas, and so on. And what we don't know is A0 on the right-hand side. And on the left-hand side, we know everything, because this is our period survival function from period life tables. So basically, what we get here is a nonlinear equation which has only one unknown, and that unknown is this A0 term, basically where our baseline intercept sits. As soon as we manage to calculate this A0, we would be able to draw each of the survival functions in each of our subpopulations. Questions?
Let's remind us what y is, please.
Y is other covariates. And we assume that they are not very important, kind of. We assume that they will average out. In fact, what will happen is that those y's will kind of get incorporated into this A0 term. Other questions? Okay. So this is what I already said. So I won't dwell on it once more. That's what I'm going to do. I'm going to solve for A0. And then I will know everything about component survival functions. Well, after I know survival functions, And because we are dealing with Gompertz distribution, we also will be able to calculate various life expectancies for our subgroups. And this middle equation just says that we are going to look at period life expectancy for particular group as the weighted life expectancies from individual groups. For instance, if I take all p-values equal 0, which means I don't have any treatment, we would obtain a hypothetical life expectancy for people who are not on treatment. And if we take all p's equal 1, we will obtain hypothetical life expectancy for a population where everyone is on treatment. And of course, we can calculate life expectancy for any intermediate value between 0 and 1. Okay? And we used this methodology to a case study on statins. But what I want to emphasize once more, this is a methodological development, as because of this, it doesn't apply only to statins. It can apply to any intervention, and it can apply to any population, as long as you have a period life table, say for particular pension. You can apply this methodology for that, as long as you put your proper survival function on the left-hand side of my equations. And of course, you can use at any intervention. It can be stop smoking, it can be uptake of statins, it can be a new cancer treatment, say, okay? Anyway, we are going to talk now about the statins. And we have actually done quite a few on statins previously with my first PhD student and then postdoc Lisanne Gitzels. In particular, we published a paper in 2016. And in that paper, we looked at 4 actually cohorts of patients at ages 60, 65, 70, and 75. But here I'm going only to use the data for 70 and 75 cohorts. And what we looked there is 2 cardiac risk groups, 10 to 19%, and above 20%, 20 to 40%, at ages 70 and 75. Those patients were born between 1920 and 1940 and observed from between 87 and 2011.
Just for the audience, can you clarify what these numbers, the Q-risk?
I was exactly going to do it, thank you, Andrew, yes. Q-risk is a standard methodology which is now used by NHS to decide whether a person needs statin prescription. And there is a web-based calculator which can calculate your Q-risk from various demographic and medical characteristics you can put in. And basically, Q-risk is a probability of getting a major cardiac event in the next 10 years. Okay? So if your Q-risk is above 10%, you are nowadays eligible for statins. Okay? Previous guideline was 20%. That's why we split those Q-risk groups 10 to 20 and then above 20. So the problem with the work we have done in that paper back from 2016 was that we fitted Cox models to each Q-risk group separately. So what we didn't have is an interaction, if any, between Q-risk group and statin. Do statins work better in some higher risk group than in lower risk groups? So we had to reanalyze this data for this study. So we basically used exactly the same models as in that paper, but we did add Q-risk group, and we also looked at the possible interaction between Q-risk and statins. And those models were adjusted for quite a few variables, including sex, birth cohort, socioeconomic status, diabetes, blood pressure, as you see, BMI, smoking. And also we put in an effect on general practice because we wanted to keep to remember that those patients from the same GP practice were more similar than people from different GP practices. So we checked for interactions, but we didn't find any interactions in this model. And we also wanted to look at the data for people with higher cardiac risk, above 40%. But we didn't have ready-made data for that. So instead, we took the data from another paper of ours, which was about heart attack survivors, as a substitute for people with high Q-risk. So we are putting together those three different risk groups. Low risk, below 20%, medium group, 20 to 40, and then high risk group, which will carry hazard ratios from MI. First of all, just a little bit of description for our 2016 data. So here at age 70, we had almost 250,000 people followed up on average for 7 years, but some people were followed up for much longer, say up to 20-something years. And at age 75, we had 194,000 people. Once more, average follow-up was 6 people. So this is kind of interesting because it shows large difference between males and females. For women, you can see that at age 70, 80% were at low cardiac risk group. And for men, only 17% were in the low risk group. So basically, there is much higher cardiac risk for males than for females at age 70. And at age 75 as well, because at age 75, 15% of women were still in low risk group, even for women, 85% were now in the moderate risk group. But for men at 75, there was just no one in the low risk group. Okay, they all were at moderate risk or higher. Now, also, if you look at the statin prescription rates, you will see that at age 70, women get much more prescriptions than males. It may be due to women just coming more often to the GP. I'm not sure. But as you see, by age 75, those are numbers in brackets, rates are kind of similar. At least in the moderate risk group, you will see that they are 19% for both males and females. Okay, this is pretty crowded table, but bear with me about the results from our two tables. So the first part, the upper part of the table, is about hazard ratios of statins for age 70 and 75. So the first two lines are for people without heart attack, and the lower third and fourth lines are for people with heart attack. And you can see that effect of statins is pretty similar at both ages. It's 0.84 hazard ratio at age 70, 0.82 at 75, and they result in similar decreases in effective age. They are the highest at age 75 for men, but basically they are changes in between 1.6 to almost 2 years in effective age. And they are much higher for heart attack survivors because the hazard ratios of statins are lower, and that evidently tells us that statins are more important in that category of patients. And those hazard ratios translate to almost 3 years, 2.5 to 3 years changes in effective age. Okay, now coming to the lower part of the table, we are looking at hazard ratios for death of cardiac risk groups. Our baseline group here is the group with moderate risk. So that's why you see 1 there. This is our baseline group. Just because majority of people at older ages will be in that age group, in that Q-risk group, sorry. So comparing low risk group to moderate risk group, you can see that hazards are lower and they translate to 1.5 to 2 years, 2 years at 70, 1.3, 1 year at about age 75. And looking at the higher risk group after heart attack, you will see that hazard ratios are much higher comparing to people who were in moderate risk group. And those translate in really big differences in effective age up to 4 years for males at age 70. Yes?
Can you clarify what the bottom group is? Heart attack, is that patients who've already had an attack?
Yes, those are patients who already had heart attack. So this is our highest cardiac risk group. They already proved they are at high risk. And you can see that if we follow them up, statins are really beneficial for those patients. And actually, how the medical guidelines went over time, this was the first group who got statins. And when we were looking at the data by 2010, about 90% of those people were prescribed statins because medical people understand that this is very important for this group. Okay?
And then does the middle group, the Q risk to greater than 20%, does that include or exclude the heart attack?
That excludes. That should be people with Q risk about 20%, but without heart attack. Yeah. Yes. Usually it will be Q risk 20 to 40.
Can I ask what about age interactions here? Because on an earlier slide, you were translating the change in effective age to a life expectancy. So I think you're assuming there that an effect, for instance, 0.8 in the top of the middle group, the effect there is going to remain constant up the age range.
It appears that that is pretty constant, at least in that age range, yes.
I guess it is the case, isn't it, that in making that life expectancy inference, we are assuming the 0.8 goes all the way up to 800.
Yes. We did check proportional hazards for those models, and they are satisfied. Yeah. So it looks like the hazard shouldn't change over time.
Same with proportional hazards, though, because my takeaway from Ilias's talk that was a runoff with time since onset of treatment or something. That was a sort of durational aspect. Was this an age interaction?
Okay. I will tell you how this data looked like. So basically, we took, say, age 70, all people. The first cohort will be all people who had at the baseline at age 70 low Q risk and no heart attack, of course, and we followed them up until we could. And we have done the same with second cohort, people at 75. So in this analysis, we have 6 distinct cohorts. People with low, medium, and heart attack, cardiac risks. And yeah, and we follow them up until they change their GP practice or drop dead.
And is that the follow was about 7 years or so?
No, I said average was 7 years, but some of them we followed up to into their 90s.
I see. So in testing the proportional hazards, the effect doesn't look to be changing with time and therefore with age.
No, it appears that in this particular study, proportional hazard assumptions are satisfied, so the hazards don't seem to be changing with time. But this is very lucky for statins. As you will hear in other talks later, our students are in much worse position, where the hazards do change over time. Okay. Other questions? Okay, let's see what we got. Okay, this is just to summarize a little bit about the, how much and what's going on there. So prevalence of risk group, we already talked that severity of cardiac risk increases with age, so that no one has low Q risk less than 10% by age 70. And by age 75, there are no male patients with Q risk under 20%. Prevalence treatments. As I said, 90% of patients after heart attack got statin prescriptions. But in a lower Q risk group, there were just 20% prescription of statins in the low risk and in 45% of patients with medium Q risk. Okay. And given the same cardiac risk groups, statins were prescribed more in women, as you have seen, but also we didn't look at it. Statins were prescribed more in younger patients than in older ages, like at age 80 or something. And also prescription rates differed by deprivation. Prescription was higher in more affluent areas. Okay. Now, first of all, we need to know what's our baseline hazards are. So here is our fit of Gompertz distributions. 2 period life tables at 2010, which were split by deprivation quintile and by sex. Males on the left, females on the right, and also you can see 5 straight lines. So the top line, the blue line, is the most affluent quintile, and the lowest is the most deprived. So you can see that baseline hazards are rather different, and they're ordered as you would expect by deprivation. So the most deprived people have much steeper line on the log scale than the more affluent people. Also, if you compare males and females, you can see that it's not that much the slope, but it's the intercept, which is different for males and females. Otherwise, females have more or less the same structure of the hazard. But basically, this picture tells us that we better fit our model separately for 2 sexes and also for different deprivation levels, because they have pretty different baseline hazards. And this is the baseline hazard in our statins model. And you can see that this is very nice and straight line, so Gompertz distribution fits our data on statins very well as well. Okay. So as I said, we are going to do quite a few subpopulations here. First of all, we do our calculations separately for each combination of Townsend score quintile by gender. So it will be 10 different period life expectancy tables. And we are going to split each of those tables into subpopulation life expectancy, depending on 3 cardiac risk groups and statins, no statins. So into 6 different life expectancies for those risk by treatment combination. Okay. So we managed to do this by solving that equation, which I showed you previously. We have an R program to do that, which we can make available, which would just ask you to put in some period life table, and it will do all the rest for you, basically, to split your population as you want. And our result is that increase in individual life expectancy due to statins is the highest in the heart attack survivors, where the difference in life expectancy is about 1.4 to 2 years, depending on age 70 or 75. Now, it doesn't differ that much between the 2 key risk groups, like low risk and medium risk result in pretty similar life expectancy, very slightly different. But of course, statins do affect both of those groups. And also the effects of statins increase with deprivation. So what we have done also, we calculated period life expectancy and its increase due to statins in each cardiac group, averaging by Townsend's co-quintiles by deprivation. So kind of for each cardiac risk groups. And I am going to show you that plot. So those are plots for life expectancy averaged over deprivation. So kind of for the whole population of England and Wales. So the first thing to note here is that the black line is the overall ONS period life expectancy. And for male, it sits kind of exactly where the green line is, which is our moderate cardiac risk group with no statins. Those people have more or less exactly period life expectancy which ONS supplies. But if you look at the top line, this is, sorry, which one is which? Sorry, let's start from the bottom line. The bottom line, the worst life expectancy, is for people who have had MI and have no statin. And the one up is a pinkish line, and that one is MI and on statin. So you can see quite a bit of difference between those 2 lines, which are due to statins for MI survivors. Yes? MI is myocardial infarction. Sorry about this. I kind of so used to using this, okay, instead of heart attack, okay. Okay, now coming to, say, comparing blue line to red line there. So red line is a low risk group and no statin, and the blue line is moderate risk group, but with statin. So what statins are doing to the moderate risk group, they kind of probe them to a lower risk group. Yeah, and if you compare effect of statins to low risk group and to moderate risk group, they give you more or less the same effect on life expectancy overall. Well, for females it's slightly different. Their ONS life expectancy, the black line, is actually more like, at least at the start, to the blue line, which is moderate risk group, but with statins, maybe because for females the statin prescriptions level are higher. Okay, any questions about this?
On the previous
The more deprived people, the more benefits from statins, yes. Because their hazards are steeper. Okay. Yeah.
I want to ask a question. To what extent is the table that you're splitting out? Thanks. To what extent is the table that you're splitting out into these different groups itself a function of a model and assumptions made about fitting the table at older ages where there was lack of data? Could that be in some way interfering with the reliability of what you're doing here at older ages?
Well, to be sincere, when we look at the period life table for England and Wales, that's big enough so that we believe that this is more or less correct. So what we have done, we just fitted Gompertz hazards to it. And we checked they don't differ much at all. They're practically bang on. Of course, if you have a smaller pension and you try to do it, you might not get it as good as we have. Was that the answer to your question?
Yes, I suppose I'm still just slightly worried that, I'm years away from doing this stuff, but when I was doing it years ago, it was always a challenge that, to get reliable data at older ages of who's actually alive and who's not alive has quite a challenge. And with the lack of data, you can end up with tables that fit remarkably well up to about age 85 or 90, and then they have very, very different cues or whatever you want to use at older ages.
Yes.
And they can't all be right,
I am aware.
So that's why I'm wondering, to what extent are you actually, if you like, finding what was deliberately put into the table by the people who did the table at older ages?
Yes, I realize this is probably a question about the oldest old and their problems, yeah. And I think that, we all understand the difficulties there. So we deliberately only fitted tables up to age 90. We didn't go after 90 because we do expect to get outliers and different behavior after 90. But I think it fits distribution up to 90 reasonably well.
I think maybe from what you were saying, maybe opposite. I think the England and Wales base table is going to be reliable, but it's more that within the data that you have lots of data at the younger ages, and then that data then fizzles out when you get to the higher ages. So perhaps if you were putting in that chart on the next page, there may be confidence intervals around these
yes.
lines, which probably get wider.
That's correct.
Right.
That's correct, yes. But in that particular study, we were looking at people born between 1920 to 1940. So by 2010, the oldest would be about 90. So we don't actually have any data on the older people. At least we didn't at that point of time. Okay. So this is restricted to age 90, yes.
I'm mindful of the time, so we need to probably...
Okay. So another thing we have done, we calculated those hypothetical life expectancy if no one were getting statins, and also if everyone got statins. And we found that the national life expectancy for women would be increased by up to 0.91 years at age 70 or 0.79 years at age 75 if all eligible women under current guideline were actually prescribed statins. And similarly, for men, the average life expectancy would have increased by 0.8 of a year if everyone who is eligible at age 70 would be prescribed statins, and if they were taking it, of course. And as strange as it is, the most improvement would come from the areas of medium deprivation, because it looks like these days more deprived areas, actually they do look after their patients, they do prescribe statins to them. It's the medium deprivation where they don't. So this is a conclusion about how much more effects of statins we can expect on life expectancy. And finally, what we are doing now, we are developing an app for general public, which can be either used by, say, health practitioners to talk to their patients about the worth of taking statins. It also can be used, say, by IFAs talking to their clients about pensions. How long do you think you need the money to last? So here we would put in various medical and socio-demographic characteristics. We use postcode here to come up with deprivation quintile, and then, as you see, we calculate BMI, we calculate Q-risk, which is exactly the same as existing Q-risk, and then we would provide life expectancy with and without statins. And we are also hoping to add other health interventions to this, so we would also add, for instance, blood pressure drugs or something like that as well. And that's it. That's all I wanted to talk about in this talk. Thank you. Questions, please?
So we're just about at lunchtime. I think we should still have a few minutes for some further questions or comments.
Thanks very much indeed. Apologies if you had already answered this when I was out of the room, in which case the answer will be much shorter. But I just wonder if you could clarify, given the very long calendar year period, how you'd allowed for these calendar year variations in mortality over the period, and whether allowing for it in different ways might change the results.
I'm not quite sure what you mean, because the slopes of the curves are based on period life expectancy table calibrated at 2010. So those slopes are calibrated to 2010.
Yeah, well, it's precisely that point, really, because I mean, that life table will only be relevant to the year 2010 to 12 or whatever the precise period is. So but your overall period was, I can't remember the exact dates now, but it was a much wider period. So your analysis would presumably take into account varying mortality over.
No, I don't, because my hazard ratios are time independent. So I can believe that my hazard ratios would apply to patients in 1990 as much as to patients in 2010.
But then could the baseline hazard be time dependent as well as age dependent? I mean, maybe that you don't need to make that assumption because of
baseline hazard can be time dependent, and we only here are talking about baseline hazard for 2010.
Sure, the reality is that the baseline hazard is time dependent. So I guess the question is how the modelling framework could take that into account.
Yes, but isn't period life expectancy is based exactly at that point in time? It doesn't look at how things will change afterwards.
Or before, but that's the whole point.
Yeah, okay, sorry. Yes?
So on your penultimate slide, you have those results for the UK population if everyone took statins. Then is there an assumption that people who are not taking statins when they're 70 are never going to take statins in the future? Or is actually in the population there probably is that change over time?
No, there is no this assumption, because from the design of that study, we only looked at patients who did or didn't take statins at, say, 70, and quite a few of them may have picked up statins later on. So this is kind of already incorporated in the model. I will take more about it, or Elias will talk more about it when we are talking about results of our landmark analysis. Because yes, you do get different results if you look at, say, a group of patients who never took statins. But of course, when you are underwriting an insurance policy, you don't know whether your client will take up statins when they're older.
Over there.
You have, so I have a couple of questions. So the first question is, so does the model work with the Gompertz-Makeham model? Does the mathematics work if you add the Makeham term to the Gompertz model?
Sorry,
So you use the Gompertz model, sort of the Gompertz/Cox model. So
yes, there is Gompertz-Makeham, yeah.
Yeah. Does the mathematics work with when you add the Makeham term?
I mean, I didn't try. In principle, the answer is that we probably could incorporate Gompertz-Makeham distribution, but it looks like Gompertz fits good enough for that age range we were interested in.
Fine. Which brings me to my next question. So the Gompertz model is a model for senescent mortality, but by definition, this is sort of non-senescent mortality, so you're incorporating some medical interventions. So I'm just curious, more fundamentally about why the Gompertz model is used. It fits nicely, but it's a model for senescent mortality only.
Well, being a statistician, I kind of try to keep away from philosophical issues like whether Gompertz model should explain senescent mortality or some other mortality. I try to keep to the data, and this data tells me that it's well described by Gompertz.
So being a demographer, it has to make demographic sense. But that aside, so the other issue is, I'm still struggling to understand, maybe we could talk a bit during lunch, but why the extra step of using the Gompertz model in the first place? So the way, how I'm seeing this is we're trying to get a sense of what's the impact of statins on life expectancy or survival. But there are other ways to do that directly without having to make any distributional assumptions.
Yes, the main issue is that you can't get from hazard ratio to life expectancy unless you know your baseline hazard. You just cannot. So you either need to find a parametric model which explains your baseline hazard, such as Gompertz, or you need to work with a baseline hazard estimated non-parametrically, which is a possibility, but it would be more complicated, I suppose.
Yeah. So, for example, just off the top of my head, could you not look at the survival of those that take statins versus those that don't, and then once we have the death rates, you could calculate any life table you desire?
There is another issue here, because I can calculate non-parametric hazards in my SIN data, but they may well be different to the hazards in the whole population. So there is also an issue of translation of one type of hazards to another. Just generally, when you can describe your data parametrically, it makes things much, much easier because you have small number of parameters to fit, basically.
Okay, so that's a priori choice. So fair enough.
Okay.
Thanks.
Okay, well, I think we should take a break there for lunch, but can we first of all thank Elena for her presentation.